Well, hello everyone. Thanks very much for the invitation to participate in this webinar series. And today is my pleasure to be talking about pesticide drift and what we can do to mitigate that. So to start with a formal definition here, pesticide drift is a part of the pesticide application that is deflected away from the target area during or following applications. And we can stick here with the visual definitions of drift if you guys prefer. We have this aerial applicator here. This picture is from Brazil, and you guys can see that it is spreading droplets everywhere, but in the soybeans here, right? So all these droplets going to the trees here, this is what we call pesticide drift. And in the other picture here in the right, you guys can see one of the worst consequences of pesticide drift. We got dicamba applications here in this field in the right, but his neighbor in the left didn't have the dicamba beans, and the wind was blowing towards his direction. So you guys can see here a lot of crop injury, right? A lot of soybean injury here. So this is one of the worst consequences when we think about pesticide drift. If we have to list the four main factors influencing pesticide drift in an application scenario, we can narrow down those four factors here. These will be the four big factors influencing drift. So we have the surrounding vegetation. So what is nearby the fields that we are spraying out there? And the wind speed plays a big role in pesticide drift potential. Boom height during applications is very important as well, as you guys will see in the following slides. And finally, the droplet size. Droplet size basically determines the drift potential in every pesticide application. This is why most of the new herbicide labels, and we are talking here about dicamba and the 2,4-D new formulations especially, they include a lot of detailed information about how we can mitigate drift and what are the rules we should follow when spraying that to minimize the risk potential. So you guys will see a lot of information regarding the buffer zones, as you guys can see here in this picture in the top, basically telling us what is the distance there that we should respect in the field borders when we are spraying out there. So the buffer zone that we need to keep when we are spraying our areas. A lot of information about the wind speed limits, the boom height limits, and most importantly here, especially in the new labels, we will see a lot of information regarding the droplet size. So these product manufacturers will include detailed information on which nozzles we can use during these applications based on the droplet size that these nozzles will produce with their products, and also the pressure range that we can use when we are spraying these herbicides out there. So if you guys take a look when you are spraying dicamba or 2,4-D and try to read the label there, you will see a lot of information regarding these aspects. You guys can see in this picture why it's very important to respect the surrounding vegetation, and especially thinking here about buffer zones. So if you guys pay attention in this picture, we have corn, we have dicamba beans, and right in the side of this field, we have these non-dicamba beans. So you guys can see that there is no buffer zone at all, right? So guess what happened? If we got dicamba applications here, you guys can see that those plants are completely healthy, right? Because they are tolerant to dicamba. But take a look in the soybeans that are susceptible to dicamba here in the very next field. So this is what we should expect when we are not respecting any sort of buffer zone. Again, I will say this a lot of times during this presentation. It's absolutely important that we follow all the recommendations there in the label if we want to avoid situations like this, because there is a reason why this information is out there. Always we need to respect the label and understand the surrounding vegetation nearby our fields when we are making pesticide applications. Another big factor that we mentioned before contributing to herbicide spray drift potential is the wind speed. Very important factor, because actually the wind that carries all those droplets from the treated area, right? So there is this data here showing that we got a 700 increase in spray drift at 90 feet when we double the wind speed. So if you guys take a look again in all these labels, they are very specific, mentioning which is the wind speed range that manufacturers recommend for these herbicide applications to be executed. And the problem with wind speed is that it's very unpredictable and very dynamic. So it's very difficult for us to try to understand and try to predict the wind in a situation out there in the field. We had this study in Nebraska, in North Platte, Nebraska, where we were spraying pesticides during a 4-hour time span. And you guys will see here in those graphs how difficult it is to understand the wind speed. So in this case here, we were monitoring the wind, the average wind, and also the wind gusts in these red lines. And you guys can see that there's a lot of things going on here, right? So the wind is not even close to being stable there. So we are talking here about an average of 13 miles per hour, but you guys will see that we have several instances that we were actually close to the 20 miles per hour, right? Or even lower wind speeds. So this graph shows how difficult it is to understand the wind speed when we are out there making these applications. And not only the wind speed, but also the wind direction as well. If you guys take a look, this is from the same study. So this is a north wind. If you guys take a look here in the 0 degrees, so it's a north wind going on. And now these dots out of the 0, out of the north, you guys will see that we are having the wind changes in direction, right? We are getting almost 30 degrees from both sides, so a total of 60 degrees of wind variation during this time span of 3 to 4 hours. So again, very difficult to understand wind. So the best scenario here is to have good judgment. If we are out there in a situation where the wind speed we are having gusts and the wind speed is changing a lot, the direction and the intensity, the best scenario here is to have good judgment and don't make applications at all if we want to stay out of trouble. The boom height is another very important factor that I mentioned before influencing pesticide drift during applications. We have this data here showing that we actually increase our drift potential in 350% when the boom height was increased from 18 to 36 inches. So you guys can see that the boom height contributes a lot to the drift potential by this data here. And this is because the higher the boom that we are operating out there in the field, the longer is the time that the droplets take to travel from the nozzle to the canopy or to the target that we are aiming during applications. So we have more opportunities there for the wind to carry these droplets off target. But this unfortunately doesn't mean that we can go out there and just drop our boom height, right? Because if you guys take a look in the nozzle manufacturer guides, we will see that there is a direct relationship between the nozzle spacing and the spray height from the target that we are working there. And this is also influenced by the nozzle angle. If you're working with a 110-degree nozzle or with an 80-degree nozzle. So unfortunately, we need to respect those rules there in the nozzle manufacturing guides. If you want to avoid situations like this, take a look in this card here in the right. So what happened here, we simulated those applications in the spray chamber out there in our lab using the wrong nozzle spacing and boom height. So you guys will see that we don't have a homogeneous spray pattern here, right? You guys will see that in the middle of this card, we are getting much more deposition compared to the sides, right? So this is why it's very important for us to keep this in mind. We need to have lower boom heights, but the lowest as possible when we check for the herbicide labels and for the nozzle manufacturer that we are using. So we want to get close to this scenario here in the left, right? With a good and homogeneous pattern, but at the same time, mitigating drift potential. Droplet size is one of the most important factors that we can manage during applications if we want to reduce pesticide drift. And how we can manage droplet size? By nozzle selection, spray pressure, and the spray solution here, thinking about the physical-chemical properties of the solution. Here we are thinking about adjuvants that we can use to mitigate drift, and also different pesticide formulations as well can have an influence on droplet size. So you guys can have a better view of this. We have these two videos here in the bottom. So we have same solution, this is just water, being sprayed with an XR nozzle at 40 psi and a TTI nozzle at 40 psi. So what we are looking here is in a fine to medium droplet size spray quality in the video in the left. And in the other video with the TTI nozzle, we have here a ultra coarse droplet size. So you guys can tell it's pretty obvious the difference between these droplet qualities, right? If you guys pay attention here, this video in the left with the XR nozzle, if you realize, you will see these black clouds hanging around in the background of this spray, right? So these are actually the fine droplets during the application, the droplets that are prone to drift. So this nozzle here produces around 20 to 25% of fine droplets with this solution that we are spraying. And when we spray the same solution with the TTI here, the TTI nozzle, at the same pressure, we get around 0.5% of fines. So you guys can see the difference here, right? It's obvious the difference between the XR nozzle with a fine to medium droplet size and around 20 to 25% of fines against the TTI nozzle. So these TTI nozzles are one of the nozzles that are listed in the dicamba labels. So this is why, right? You guys can see that the droplet size is much larger compared to the other nozzle. To help us understand the droplet size scenarios during pesticide applications, the industry came up with this very nice color-coded droplet size guide for us, so we can understand what droplets we are producing for different nozzles and solutions. They are based on the VMD, and if you guys take a look here in this graph in the left, the VMD is the droplet size that divides our spray volume in half. So this droplet size classification is based on that value. And basically here we go, most of the applications in agriculture go from the very fine droplet size up to the ultra coarse. Very fine, and medium, we are thinking more about the fungicide applications, insecticide applications, and even some contact herbicide applications. So when we need a nice coverage in our application, we are considering these droplet size ranges here. So we need a lot of droplets per area. And when we are working with systemic products like glyphosate, 2,4-D, dicamba, we can use bigger droplets because the coverage is important, but not as important as in a contact product. One of the things that we do in our lab out there in Nebraska is to understand the droplet size of different nozzles and tank solutions in different pressures. So we have the laser diffraction system there that actually tells us exactly what droplet size we're spraying on there. So we did this series of simulations with different nozzles and pressures, so you guys can understand how important understanding that is if we want to mitigate drift. So first, in this simulation here, we started spraying just water here with the XR110 025 nozzle at 60 psi, so using a higher pressure here, just with water. And when we analyze this with our laser diffraction system, we got that around 25% of these droplets, 25 to 26% of these droplets were fines, so less than 150 microns. So how can we mitigate that? How we can increase this droplet size? One of the strategies here is basically just dropping the pressure. So remember, we were working with 60 psi, right? Now we are just working with 30 psi, so half of the pressure. And take a look what happened with the fines. Same solution, same nozzle. We reduced from 27%, 26% to 15% of fines, just reducing the pressure here. But you can still do a better job in reducing that. Now what we are doing, we are increasing the orifice size. So instead of working with the 025, now we are working with the 05 at still 30 psi. And take a look in our fines, just 7.5% now. So we start with 26%. We dropped to 15%, and now we've dropped it even more to 7% of fines. Just changing the nozzle, and the nozzle orifice size, not even the nozzle type, and the pressure that we are using. So this is what happens when we change nozzles now, the nozzle design. So instead of using an XR nozzle, we are using the TT nozzle here. Those nozzles were very popular when glyphosate was released because they do a better job in mitigating drift. So take a look, now we are down to 3% of fines. Just changing nozzle here, guys. And we can do still do a better job here. Now we are working with the TTI nozzle. So we changed the nozzle here, same orifice size, the 05s at 30 psi. And take a look in the percent of fines we have now, just 0.2%. So remember, we started from 26% in just changing nozzle design, orifice size, and operating pressure. Instead of having 26% of fines, we are down to 0.2% of fines. This is a drift study that we did in our laboratory to show how important nozzle selection is for droplet size and consequently for drift potential. So what we did there, we did these pesticide applications within our wind tunnel. We have a wind tunnel that is 40 feet long, so we can have drift stations in different downwind distances from the nozzle there. So we can collect the drift deposition in different distances and compare them with different nozzles or different solutions. So if you guys take a look here in this graph, in the top, we will see that in the y-axis we have the spray deposition, the percentage of what we sprayed. In the x-axis we have here the different downwind distances from the nozzle. So they go from 1 foot from the nozzle up to 12 meters. So we are talking about roughly 40 feet here. We did these applications with 2 different nozzles. The TP nozzle is very similar to the XR nozzle, so we are producing fine droplets here. And with the AI nozzle, producing ultra coarse droplets. So you guys will see here the drift profile of these 2 different nozzles. The red line would be the TP nozzle, so the fine droplets. And the black line would be the AI nozzle with the air inclusion system and the ultra coarse droplets. And you guys can see here that we consistently had more drift, more deposition with the flat fan nozzle, right? With the TP nozzle. We can see this as well in these water sensitive cards that we had in the different downwind distances from the nozzle. So you guys will see that the card here closer to the left will be closer to the nozzle, and the one in the right here would be the far away from the nozzle in the 40 feet distance. And you guys can see the drift profile with the flat fan nozzle, the TP nozzle, and the drift profile with the air inclusion nozzle, right? So totally different. And so we fit some statistical models in this data, and we can understand, for example, what is the distance from the nozzle that we are still having 1% of drift. 1%, if you guys think about 2,4-D or dicamba, is a lot. So this is why we're using this parameter. So when we did these applications with the fine droplets with the TP nozzle, we were having 1% of spray drift up to 20 meters from the nozzle. So we are talking here about 60 feet. When we changed the nozzle, so same operating pressure, same solution, take a look how much we reduced that. Almost 5-fold, right? So again, this also shows us how important it is to manage our nozzle selection if you want to reduce pesticide drift. We can also use adjuvants to manage droplet size and therefore decrease the drift potential from our applications. So you guys will see here in this slide that we tested 21 different treatments, including different herbicides and different adjuvants. We sprayed them with the same nozzle. The nozzle that we check in the TJAP catalog would produce medium droplets. But remember, all the information in these catalogs are based on applications with water. So what happens now when we are spraying different herbicides with different adjuvants? So you guys can see here for several instances, we were able to change the droplet size classification from medium to coarse droplets because of the adjuvants. So the adjuvants increase the droplet size, so help us mitigate drift potential. And we guys can also see that for some instances, we didn't change the droplet size that much, right? The droplet size was still classified as medium. And for a few instances here, especially in treatment number 12 and 11, we actually decreased the droplet size. So droplets, instead of medium, they pass through to fine droplet classification. So we were actually increasing our drift potential for these applications. So what we can see in this slide is that, yes, the adjuvants can be very helpful in managing droplet size when we talk about increasing the droplet size to mitigate drift. But they need to be tested because adjuvants will work differently for different nozzles and different herbicide solutions. So it's very important that we test them. Pesticide formulation can also influence droplet size when we are spraying pesticides. This is a study from a former student that we had in our lab. Very interesting study here. So what we did here, we sprayed glyphosate, and we're trying to understand the percent of fines during this application. This is with AI-XR nozzle. And if you guys take a look, we were producing around 30% of fines with just glyphosate here. Then we sprayed just 2,4-D, and you guys can see that we were getting around in between 15–20% of fines. Then what we did, we mixed those two herbicides. And so you guys can see here in this purple ball, this is the glyphosate plus 2,4-D mixture. And you guys can see, obviously, we were in between these, right? Since we were mixing the two products, so around 20–22% of fines. But then we compared this tank mixture that we did in the lab with a pre-mixture. This is, now we are talking about the Enlist Duo formulation. This is glyphosate plus 2,4-D from Corteva. And take a look in the percent of fines when we analyze the pre-mixture formulation. So instead of having 25% of fines, now we are close to 10%. So this actually shows us how important it is to manage, for these companies to manage the herbicide formulations in order to mitigate drift. Talking about the same products here, what we did, we also tried to understand the drift potential of these different tank mixtures out there in the field. So for the black balls here, the black dots, this is the tank mixture that we did by mixing the two products. And then we compared the drift potential with Enlist Duo, or the pre-mixture formulation. So you guys will see here in the y-axis the fraction of apply of the application, and in the x-axis the downwind distance from the treated area. And you guys can see, analyzing these drift curves, these drift profiles, that we consistently had more drift when we were working with the tank mixture compared to the pre-formulation, right? So again, herbicide and pesticide formulations can also influence herbicide drift potential. And this is where we can gather all the information that we covered in this presentation. The herbicide labels. If you guys take a look, especially the new products labels, we're talking here about the new dicamba formulations, the new 2,4-D formulations. They include detailed information about everything we talked here during this talk. They are talking about the buffer requirements, talking about the surrounding vegetation. So for example, we have here some restrictions if we have, for example, a sensitive crop, so we cannot apply. We're talking here about sensitive beans or other crops. We have very detailed information about the nozzle selection that we can do, the operating pressure that we can use, information regarding the boom height. So for example, here, this is a section from the XtendMax label. You guys can see here, it's the recommendation. Don't spray over 24 inches above canopy. And also information detailing the environmental requirements as well. Talking here about the wind speed. So in between 3 miles per hour and 10 miles per hour. The temperature inversions here is very important as well. If you want to avoid problems with drift, this is more common when we have lower wind speeds. So again, the herbicide labels and pesticide labels in general include a lot of information here to help us understanding the drift potential of our applications and how to mitigate that. So these are the take-home messages from this talk. First of all, drift will always happen. Mitigating drift is essential, so we need to use all these strategies and technologies we talked about during this talk to make sure we do a good job in mitigating drift. Nozzle selection has the greatest influence on particle size because this directly changes the droplet size spectrum. We need to pay attention to the sensitive vegetation in the surrounding areas as well, especially if we want to stay out of trouble with the new technologies, talking here about dicamba and 2,4-D, but also other technologies like glyphosate and any pesticide in general. When we think about the wind speed, there is no substitute for the common sense. If the wind is blowing, droplets will move. And it doesn't matter if you go there in the report during our applications and mention that the wind speed was steady at 6–7 miles per hour. Trust me, if we have any drift incident, they will figure out how was the wind speed during that time. The drift can also be influenced by pesticide formulation. And we are talking here not only for physical movement of particles, but also volatility, but that's another topic. And finally, adjuvants can reduce drift potential, but they need to be tested. And this is a big part of what we do in the pesticide application technology lab. We work with different companies to try to understand and test their products so we can generate quality data. And this is exactly the topic of our next speaker, Ed. We work in partnership with his company, testing their new adjuvant technologies, and he will talk more about this in his talk. With that, I want to say thanks to everybody for sticking around, and I'll be glad to take some questions here if you guys have. Thank you very much for the opportunity.